So in this lecture, we'll talk about the concept called homoscedasticity, heteroscedasticity, and the Gauss-Markov assumptions. The background to this lecture and the reason we need to discuss this concept are the following. We have a setup that we talked about a few times, the linear regression model with random sampling. So we have yi is equal to beta 1 plus beta 2 xi plus an error term. If I only start with the linear regression model and make no other assumptions, then the OLS estimator could be absolutely terrible. There's no reason for it to work. The minimum assumption that we need for the OLS estimator to have some nice properties is the exogeneity assumption. And we now know that if we make this assumption that the errors on average is 0 no matter what the value of x is, then the OLS estimators B1 and B2, they have this very nice property of being unbiased, on average correct, and consistent. Now we can actually dig further into this discussion and find even nicer properties of the OLS estimator, but that requires a little bit more assumptions. And these assumptions are related to the variance of the error term. So far we haven't said anything about the variance of the error term. All we've said is that it must have an expected value of 0 conditionally on x. So let's move down then to the variance, and which is related to these homo and heteroscedasticity. So we say that the error terms are homoscedastic if the error terms have a constant variance conditionally on x. So if the variance of epsilon I given xi is sigma square, that's the symbol we use, no matter what I is, every error term has the same variance, then we say that they are homoscedastic. Homo being meaning the same, so the variances are the same. So they all have the same variance conditionally on x. If they're not homoscedastic, that is, if every error term has its own variance, then we call them heteroscedastic. Hetero meaning here different. So let's illustrate these two cases in an Excel sheet. So I have in this case just 10 observations. That's enough to show this. I have just simulated some x data. In this case I've just used the rand function of Excel, multiply that by 100. So every x value is just any random number between 0 and 100. And let me first illustrate the case we have started with, that is homoscedasticity. So the error term should have a constant variance. So to simulate homoscedastic errors, I can just type norm dot env rand. I'm going to get now from the normal distribution. The exogeneity assumption requires me to put a 0 here. This must be 0. But like we talked about, there are no restrictions on the standard deviation. That can be anything from 0 going up. The bigger it is, the harder it is to estimate the model, but we can put anything. So if I put 1 here, hit enter, copy this down. Now since I've copied this down, there is a 1 also in C3, and there is a 1 in C4 and a 1 in C5 and so on. So these are all drawn from the same normal distribution, the same standard normal distribution. So these are homoscedastic errors because they have the same variance 1. So let's add that. Let's write homo epsilon, and let's put here hetero epsilon. So to get heteroscedastic error terms, we need to simulate these errors such that they have a different variance. The variance must be different between them. One way I can do that is just to write norm.inv and rand to give me normally distributed random numbers. I can put, or I have to put, a 0 here because I still want the heteroscedastic error terms to be, I still want the x variables to be exogenous. And here I can put, instead of 1, I can use my x variable. So if I put here, say, x over, I can't use x because that will be too high a variance for the error terms, but I can use x over 100, like that. But of course I can't use x, I have not named it, but I can use b2. So this is the error term for this guy. Copy this down. And I now have heteroscedastic error terms. We'll see later that this is a very common way of modeling economic data. If I have economic data, let's say data over countries, for example, it's very unrealistic to think that the error term affecting, let's say, Luxembourg is the same as the error term affecting a large country such as the United States. We'll revisit this topic later on, and for now the purpose is just to understand the difference between homoscedastic errors. They all have the same variance. Heteroscedastic errors, they have different variances. Of course, you don't have to model the variances such that the standard deviation is precisely the corresponding x value. You can model it differently as long as the variance is different. I have now increased the number of observations to 50, so we can make a graph of this and see the difference between homoscedastic and heteroscedastic errors. So if I start by plotting the homoscedastic errors, it looks like this. Homoscedastic errors. We have x on the x-axis going from 0 to 100, and we have the error term on the y-axis. They are somewhere between -3 and 3, and in this case the variance of each error term is the same. It's 1, no matter what the x value is. So they are sort of evenly distributed in this scatter plot. The scatter plot of the heteroscedastic residuals will look very different. So let's mark these guys. Control, Shift Control down, and then do insert, scatter, and like that. These are the heteroscedastic residuals. And now you can clearly see the heteroscedasticity. In this case, the error term has a variance that depends on x. So the further you go to the right, the higher is the variance of the error term. And you can clearly see this in the diagram. We see that now the scatter plot is sort of inside this kind of shape, like a funnel or a vuvuzela or some shape like that, trumpet maybe. And that's simply because the error terms here over when x is large have a larger variance. Over here they have a smaller variance. So there's less spread in the error terms to the left and more spread to the right. And the idea here is simply that if this was a scatter plot using countries, then we have large countries to the right with larger error terms and small countries to the left. Alright, so now we understand a little bit about heteroscedasticity, a varying variance. We can now discuss the Gauss-Markov assumptions. So the Gauss-Markov assumptions for the linear regression model with random sampling is then the collection of these two assumptions that we've been talking about now. It is, first of all, the explanatory variable is exogenous. That is going to guarantee unbiasedness and consistency of the OLS estimator. And the second assumption of Gauss-Markov is that the error terms are homoscedastic. That is, these guys do not satisfy Gauss-Markov. These guys do satisfy Gauss-Markov. We will then see that we can say a whole lot more about the OLS estimators if the Gauss-Markov assumptions are satisfied. And things gets a little bit more tricky if the data is heteroscedastic, a topic we will revisit later.